Hello everyone and welcome back to this video and those very exciting exercises, numerical examples related to electromechanical conversion systems. And as I said before in the previous videos, the induced EMF, electromotive force, is a very important element to understand the mechanism of generating AC signals. So today in this video we are dedicated to obtain some calculations, some results related to this induced or generated EMF. So without further delay, let's start with this statement over here. Consider a rectangular coil and the size of these coils are 12 centimeters and 8 centimeters. And this coil is rotated in a magnetic flux density. You can see over here the numerical value, 1.4. The longer side, 12 centimeter of the coil, actually cutting these flux. And the coil comprises of 80 turns and is rotating at 1200 RPM or revolution per minute. So there are two questions over here, very simple. The first one is to calculate the maximum generated electromotive force or induced voltage in volts. And second, if the coil generates 90 volts, what should be the speed, in this case the velocity in meters per second, that this coil should rotate? So as you can see over here, we have the numerical results, and in the first case you can see that the maximum voltage generated, in this case is an instantaneous voltage, is 135.11 volts. And you can see over here the result of the velocity to induce 90 volts. In this case is 3.3480 meters per second. So without further delay, let's start the solution of this lovely problem. So what you need to know is, or what you need to remember first is, in the theory, I explained to you this equation number 7. And in this equation number 7, what is telling you is that the total induced voltage in volts in one coil is twice the number of turns multiplied by the magnitude of the flux density in Tesla multiplied by the length of the conductor cutting the flux, multiplied by the velocity in meters per second, and multiplied by the sine of theta, where theta is the angle between the relative motion and of the conductor and the magnetic field. So now what we need to do is very simple, because the first step here is that we want to know what is the induced voltage when this is working at 1200 RPM. So the first thing that we need to understand is that the data that is provided in this example is 1200 RPM or revolutions per minute. So in order to use the equation 7 that I already presented above, what we need to do is convert the rotational speed into linear speed, in this case meters per second. So there is equation, very simple equation, everyone must remember from mechanical or from physics, that the linear speed is related to the rotational speed and the radius of this circular motion. And in this case, you must remember that the radius is the diameter divided by 2. So in this case, the diameter is 0.08 meters. And over here, we are dividing by 2 in order to get the radius. So what we need to do now is convert the 1200 RPM or revolution per minute into meters. So to do that, what we need to do is basically divide 1 by 60 in order to disappear the minutes, and then to disappear the radians, multiply by 2 radians. So we obtain here that the linear speed or velocity will be 1.65 meters per second. Or directly coming from the calculator, you can see that the speed in this case, or the velocity, is 5.02 meters per second. So now, in order to obtain the induced voltage, to be honest, is a very simple exercise because it's a numerical substitution. In this case, you must remember that the relative motion of the conductor and this coil is basically 90 degrees. So if you remember the equation number 7, there is a term on the right hand side that is the sine of this angle theta. But if the angle is 90 degrees between the motion and the magnetic field, so the sine of theta is numerical to 1. So we obtain this equation 2n multiplied by b, l, and v. So the numerical substitution is over here. You can see the numbers: 280 torrents, the magnetic flux density 1.4 teslas, and you can see over here 0.12 meters. And you can see over here, this is the speed, linear speed that we calculated before, and the sine of 90 is 1. So finally over here, you can see that the induced voltage finally is 135.1 volts. And you must remember this is an instantaneous value. The second part of this problem is extremely simple, because it's again using the same equation that we have been discussing. Again, is the induced voltage equation, the equation number 7. But now what we want to do is to obtain the velocity that allow an induction of 90 volts. So what we are doing here is basically extracting from equation number 7 the velocity, and from there you can see that the velocity will be the induced voltage twice the number of turns, the magnetic flux density, the length, and the sine of the angle theta. But again, the relative motion and the magnetic flux density, they are in perpendicular, so there is 90 degrees, so the sine of 90 degrees is 1. So finally, what we need to do is substitute the numerical values here in this equation. You can see in the numerator 90 volts. You can see here in the denominator 80 turns from the number of turns, 1.4 Tesla for the magnetic flux density, 0.12 meters for the length, and the sine of the angle 90, that is 1. So finally, you can see over here 3.34 meters per second. That is the linear speed that we need to move this coil inside this magnetic flux density. So it is a very simple example. In this case, the most important equation is over here, is the induced voltage. You can see the N mean here the number of turns inside the coil, and you must be careful with this angle because this angle is the angle between V and B. In other words, the angle between the relative motion and the magnetic flux density. So we reached the end of this video today. This has been a very simple example, numerical example related to induced voltage. And I hope you enjoyed the explanation and you find this useful, and this clarify any doubts that you have regarding this very important equation. And if you have any question, please leave a comment here or drop an email. I will be extremely happy to support you and help you. And if you like the video, remember to like or subscribe to the YouTube channel. Well, thank you very much for watching, and that's all for now. And I will see you very soon. Bye now.